In this chapter, we will cover data and graphing of one stress-strain spoke test, good and bad disc brake wheel design, part 2, the imperative to avoid exceeding spoke elastic yield points, apparent impact of using spokes with a thick diameter, the relationship between hub dimensions and developing forces, special considerations for carbon composite rims, and then an outlandish proposed experiment. In this chapter, we're going to go from the deceleration of disc brake wheels into a discussion of spoke elasticity and strength, and then we'll go back to that topic and I'll give you my takeaways and concerns. This is a picture of a Supreme race spoke. You can see that it is 2 millimeters in diameter at the ends and narrows down to 1.8 millimeters in the midsection. I took a bunch of these and cut off the ends and used a constant diameter 1.8 millimeter part to do some load testing and tensile strength testing at the engineering lab at Duke University. Here's a graph of the recorded data. On the x-axis is strain, and on the y-axis is engineering stress measured in newtons per square millimeter. I can also measure strain as percent strain, and when I do 0.002 becomes 0.2%, 0.004 becomes 0.4%, and I can add a couple more lines. That would be 0.1%, and that would be 0.3%. We have a very good fit of a straight line to this curve between 0.1% and 0.3%. This is some setup data about the Tinius-Olson load cell that was used, and we're going to get data recorded as force in newtons, displacement in millimeters, and strain as a percent. As the force on the spoke was steadily increased, over 500 readings were taken of those three numbers. This is some of the very preliminary data as the load cell is just beginning to start to put tension on the spoke. This is the first part of the data that I have cut and pasted so we can look at it, and these columns are force, displacement, and strain. And this is the point here at 430 newtons that we have a 0.1% strain. The second column continues the first column. If you look at the bottom of the first column, the last recorded entry is at 800 newtons, and at the top of the second column we continue with 813. Similarly, the third column continues the second one, and if you look here, you see that at 1,378 newtons we have reached 0.3% strain. Just to focus on those 2 points, I pulled the data out. There are the data points that we just looked at, and I could also measure my starting area of 2.54 millimeters squared, and I can compute now my stress, which is going to be 169 newtons per square millimeter at 430 newtons and 542 newtons per square millimeter at 1,378 newtons. Here you can see the stress recorded on the y-axis for those 2 key points. Going back to the table, we can see that at 1,597 newtons we have 0.35% strain. And at 0.35%, we can see that our line of recorded data has moved away from the straight line we were looking at, and we have now entered possibly into an area of semi-plastic deformation of the spoke. In other words, we appear to have exceeded the spoke's yield point. At 1,795 newtons, we're at 0.4%. At that 0.4% strain and the accompanying stress of 707 newtons per square millimeter, we have to start thinking about irreversible changes in the composition of the spoke. This is the same wheel we looked at before, where 12 of the spokes are radially laced and only the other 12 are tangentially laced and can stop the wheel from turning when the disc brake stops the hub. Only the pulling spokes in blue and pushing spokes in red can do that. If the wheel is made out of Supreme race spokes, which have an initial cross-sectional area of 2.54 millimeters squared, I should be able to take my static tension and look it up in the data that we've got and then see where it lies on the stress-strain curve. Here's 1175 newtons and a percent strain of 0.25. Here's our point of 0.25% strain, which is very comfortably within the perfectly elastic region of 0.1% to 0.3%. But this dynamic stopping tension number looks like it might be problematic. That data point there is indicating a strain of about 0.35%. At 0.35%, we may have gone beyond the yield point of the spoke. Let's look at some takeaways on wheels with disc brakes that we can take from this discussion. Here's the first one. Both sides of a wheel must be laced with tangential braking spokes. Here's a picture that you've seen before, and we see that the red spoke is a pulling spoke that can transfer torque when you stop the hub and the wheel wants to keep turning, and those are tangentially laced. They should be that way on both sides of the wheel for both the front and rear. Just a reminder of what we mean by tangential lacing. Let's put a line extending the spoke like that on each wheel, and that circle there represents the whole circle diameter of the hub. That's the radius, and these right angles give us the best torque transfer angle. The spokes are tangent to the circles representing the whole flange diameter of the hub flanges. Secondly, pulling spokes when braking should be laced heads in. The red spoke, you see the body of the spoke is on the outside of the flange, which means that the head is on the inside of the flange. Conversely, these are the pushing spokes. They have to be laced in the other direction. So in the case of the pushing spokes, here we see the head is out and the body of the spoke is inside the flange. By lacing my pulling spokes, shown in red, heads in, the body of the spoke being on the outside of the flange, gives me the widest angle with the rim, and that gives me the best lateral support of the wheel when braking. In the first comment I said both sides of the wheel must be laced up with tangential braking spokes. In the second I said that the pulling spokes should be laced heads in. If the pulling spokes and the pushing spokes are reversed in terms of their head orientation, it's not a fatal flaw. So of those two, number one is the most important, with tangential braking spokes on both sides of both wheels. Third, torque and power transfer are much greater when braking than accelerating. That certainly will be under extreme conditions, not necessarily the case, but if you have to make an emergency stop, you can certainly stop the bike much faster than you can bring it up to that same velocity when accelerating, starting from a dead stop. Fourth, although the increased tension on spokes during braking does not risk fracturing them, it may take them outside of their elastic region. And that would mean that some of the stretching of the spoke would represent a permanent deformation of the spoke, and that would necessarily mean that the tension on the spoke would go down, and that could set in motion a series of cascading events that would destroy the wheel. And lastly, I would have some structural concerns from the enormous force on the hub flanges and the rims. So in addition to the aforementioned concerns about the spokes themselves, I think I'd start worrying about metal fatigue and the possibility of a spoke either cracking the rim or pulling through the rim, or at the hub, the possibility of a piece of the flange eventually breaking off. Considering disc brake wheels as a whole, it's fair to ask, what is the weak link in the proverbial chain? Is it in the spokes, the rim, the hub, or the nipples? Let's try to answer that for a lightweight, low spoke count wheel, because there is certainly going to be a demand for that type of wheel. With respect to spokes, we already talked about the problem of spoke tension possibly going beyond the yield point of the spokes. There's also the possibility of repeated metal fatigue causing breakage at the spoke elbow. Unquestionably, with the rims, there's concern about cracks and the possibility even of nipples pulling right through the rim. Hubs will have to be made strong enough to be able to support through the flanges the enormous tension on the spokes. And then there's the question of nipples, which I think probably can be dealt with by making sure that we use always spokes of the correct length so that we have full overlap of the threads of the nipple with the threads of the spoke. Failure of a nipple is very rare, so I think we can take that one out. The weak link here is going to probably vary from one manufacturer to another and one wheel to another, but I think we know some things that can help mitigate the possibility of a failure at some point. A few design considerations with respect to spokes and the lacing. All spokes should be tangential. The number of spokes sufficient to safely spread the load in the worst case scenario, and spokes with a high elastic modulus. Another is spoke diameter, and this requires a little explanation. Here we see three spokes. The top one is a straight gauge 2mm spoke. The middle one is double butted with a middle section of 1.8 millimeters, and the bottom double butted also with a middle section of 1.5 millimeters. All three spokes are sufficiently thick at the elbow where the stress concentration is great. All three spokes are made of stainless steel. Here's the same stress-strain curve we've seen before. Remember that stress is measured in newtons per square millimeter on this graph. These are the three spokes we want to compare, and these are the cross-sectional areas, which for each one would be A0. For the time being, we're going to make an assumption that all three have the same elastic modulus of 200 gigapascals. Here's my formula for the elastic modulus. For each of these spokes, what I want to know is what is the force on the spoke at the point that it reaches 0.3% strain. We define 0.3% in this case as our yield point, after which the curve and straight line are no longer congruent. In the formula, we replace strain with 0.003. This equation is not very hard to solve, but there's a lot of powers of 10 that can be confusing. So let me work the first one out for you in the case of the force with the 2mm spoke. Remember that a Pascal is a Newton per square meter, so when I rearrange that, I get that the force on the 2mm spoke divided by its unit cross-sectional area is equal to 200 times 10 to the 9th newtons per square meter times 0.003. Multiplying both sides by A0, I get the expression shown. Remember that A0 is 3.14 square millimeters, but I have to convert that to square meters, so it becomes 3.14 times 10 to the minus 6th square meters. And when I multiply that out, I get a force of 1,884 newtons. If I go from my 0.3% point on the graph over to the y-axis, I find I have 600 newtons per square millimeter. And in fact, 1884 newtons divided by 3.14 square millimeters is equal to 600 newtons per square millimeter. When I solve the same equation for my 1.8 millimeter spoke, I get the force is equal to 1,524 newtons. And for the 1.5 millimeter spoke, I get 1062. Let me just make a couple more comments just so we don't miss the point of this discussion. The first point is that since we define the modulus of elasticity of being 200 gigapascals for all three of these spokes, then at least in their elastic region between 0.1 and 0.3, all three will have an identical graph. The second point is that the engineering stress defined as newtons per square millimeter is the same for all three spokes at 0.3%. And the last point is that in a disc brake wheel, because of the concern about the very large amount of tension that develops on the pulling spokes, the thicker spoke would appear to be a better option because its yield point occurs at a higher number of newtons of tension on the spoke. And because that is not obvious, let me explain exactly what I mean. I'm rolling along and I have to make an emergency stop, and I want to see what happens inside this dotted circle here. I say to my bike, give me 1,700 newtons of stopping force now, and that's going to be on each pulling spoke. Now, there's my formula for elastic modulus, which is sigma over epsilon, and my epsilon becomes 1,700 newtons divided by 200 times 10 to the 9th newtons per square meter times the cross-sectional area of the spoke. These are my three spokes, and these are my three cross-sectional areas. And what I want to do is calculate epsilon, the strain, for each of those different spokes with that amount of applied force. For my 3.14 millimeter spoke, when I calculate that out, I get epsilon is equal to 0.0027, which is 0.27%. 0.27% on my stress strain curve is clearly within the elastic region of the spoke. For my second spoke, with a cross-sectional area of 2.54 square millimeters, I calculate epsilon and I get 0.0033, which is 0.33%. And at 0.33%, with that gigantic force, I may have gone a little bit beyond my yield point. For my third spoke, with a cross-sectional area of 1.77 square millimeters, I get a strain of 0.0048, which is 0.48%. And that would appear to be indisputably beyond my yield point. So I can see that my thicker spoke can transfer the force I need with a minimum amount of extensional strain. Of course, the thicker spokes are going to be heavier, so once again we have competing objectives, and we have to decide whether the strength of the wheel is more important than the weight. And one last comment before moving on. We said here in this discussion that the modulus of elasticity of all three spokes was 200 gigapascals. If in fact the thinner spokes, because they have been worked, have a higher modulus of elasticity, then the benefit that you get from a thicker spoke becomes somewhat less. For rims, strong nipple beds with reinforced holes and or reinforcing washers to spread out pressure concentration points. Later in the discussion about carbon composite rims, you'll see that there is perhaps a very strong advantage to carbon fiber for disc brake rims because of the fact that it's possible, without increasing the mass very much, to selectively reinforce the rim in strategic points where the concentration of stress is the greatest. And lastly, the hub, reinforced flanges to prevent flange cracking, and flanges with larger hole-to-hole diameters to improve angles. Let's work through an example of how a larger hole-to-hole diameter can be an advantage. This is the problem we worked out a minute ago with a hole-to-hole diameter of 42 millimeters in the hub and a radius of 21 millimeters. We found that our total tension had to increase by 2,278 newtons. But if I have a hole-to-hole diameter of 58 millimeters or radius of 29, then my angle is larger. Theta is 5.74 degrees instead, and so I have a better angle at which to pull the rim backwards, and the total tension does not increase by as much. For ease of comparison, we see both wheels here, and starting with the one on the top with this smaller hole-to-hole flange diameter, we have a smaller angle theta, and that gives us a smaller sine. We divide by that smaller sine and we get the larger quotient. The wheel at the bottom has a larger hole-to-hole flange diameter, and so I have a larger angle here, theta, larger sine, larger divisor, and a smaller quotient. So by going from a smaller hole-to-hole flange diameter to a larger one, I decrease the tension that the spokes have to increase by about 30%. Of course, a larger flange is going to mean more metal in the hub and a heavier hub. A good analogy for understanding all of this is the following problem. I have a flagpole which is lying on the ground. Here is the base of the flagpole, here is the end of it, and my job is to raise it to a vertical position. I attach a rope to the end of the flagpole and pull on it with a force represented by that vector. That vector at angle theta can be resolved into a horizontal and a vertical component. The vertical component can also be shown at the end of the flagpole, and it's clear from the picture that it's going to be hard to exert a force to raise the flagpole from the angle shown. But if I stand on some type of a platform, I have a larger angle theta, and I can get the same magnitude of vertical force by applying less tension to the rope. So I can compare directly the problem of the small angles of raising the flagpole with the small angles of generating reverse torque on the bicycle wheel. It might even look a little better to you if I show it like this. Here is a set of wheels that I have good expectations for. We have White Industries MI6 disc brake hubs, a nice big 60 millimeter hole-to-hole flange diameter on both sides of both hubs, and I laced these up to Velocity blunt SL rims, tangential lacing on both sides of both wheels, and nice high tension. Good strong hubs and rims should make for a good strong wheel set. And here are some close-up photos in case you want to look at them of the left and right flanges of both the rear wheel on the left two photos, and the front wheel on the right two photos. We're at a position now that we should be able to compare two wheels and glean some interesting information about the engineering decisions that were used. So we're going to compare a rim brake wheel and a disc brake wheel. Both are MV composite wheels. The rim brake wheel with 28 spokes is built with a 2-cross, even though it could have been built with a 3-cross. This spoke crosses this spoke and this spoke. The 2-cross pattern gives sufficient tangential spoking for pulling spokes when the wheel accelerates, but better lateral stability than would be the case with a 3-cross. The disc brake wheel with 24 spokes is nevertheless built with a 3-cross pattern, which is very unusual. This spoke shown in red crosses this spoke, and this spoke. Shown here in blue is the whole flange circle, and you can see that by using a 3-cross pattern, I get my pulling spoke tangent to that circle, and that greatly improves the torque transfer. Very importantly, the spokes that are heads in are able to clear the heads out of the neighboring spokes so that there's no interference of one spoke lying on top of the other. Here is a picture of the rim, and you can see that it is clearly intended to be used only in a disc brake wheel. You've seen here some good examples of keeping things in balance. Oftentimes when you try to improve one situation, you make another one worse. So the art of designing the wheel is understanding all of these variables and coming up with the best combination depending on the type of wheel you want. At this point, if you're kind of mentally exhausted, you can relax for a minute as we just have a little bit of fun in the remaining half dozen or so slides. This fourth column picks things up several minutes later when our force has gotten all the way up to 35-45 newtons with a 1.76% strain. At this point, the metal in the spoke has gone way beyond the yield point, obviously, and it can't even stretch any farther without totally disintegrating. So we see as we continue to stretch the spoke, the recorded force actually starts to go down, and finally at this point here, the spoke can't do anything except just break. It's still true, however, that at 35-45 newtons, our spoke has not yet broken, although it's getting close. Let's say I take 4 spokes at 3,500 newtons each. I get a total of 14,000 newtons. So my question is, how much vertical dead weight could 14,000 newtons hold up? Well, 1 newton is 0.225 pounds. 14,000 newtons would be 3,150 pounds. Well, here's a Toyota Corolla at 2,800 pounds. Can I hold this up with 4 spokes? Well, this doesn't look so hard. I can use some type of a crane and build a frame to support the car. There's the frame. And I'm going to put a spoke on each corner of the frame and then to the bottom of each spoke running around the front of the car and to the back, some type of a strap to then be able to raise the car. Now I'm ready to crank up the car using the crane. I've got to make sure I don't exceed 3,500 newtons or 788 pounds on any one spoke. I know there's going to be a little bit more weight on the front of the car than the rear because of where the engine is located, but I might be able to balance it out to have something like this: 780 pounds on each of the front spokes and 620 on each of the rear spokes. That gives me a total of 2,800 pounds, the total weight of the car. At some point, I'm just going to have to try this and see if it works.